Fluorescence is the emission of light by a substance that has absorbed light or other electromagnetic radiation. It is a form of luminescence. In most cases, the emitted light has a longer wavelength, and therefore lower energy, than the absorbed radiation. The most striking example of fluorescence occurs when the absorbed radiation is in the ultraviolet region of the spectrum, and thus invisible to the human eye, while the emitted light is in the visible region, which gives the fluorescent substance a distinct color that can only be seen when exposed to UV light. However, unlike phosphorescence, where the substance would continue to glow and emit light for some time after the radiation source has been turned off, fluorescent materials would cease to glow immediately upon removal of the excitation source. Hence, it is not a persistent phenomenon. Fluorescence has many practical applications, including mineralogy, gemology, chemical sensors, fluorescent labeling, dyes, biological detectors, cosmic ray detection, and, most commonly, fluorescent lamps. Fluorescence also occurs frequently in nature in some minerals and in various biological states in many branches of the animal kingdom. History. An early observation of fluorescence was described in 1560 by Bernardino de Sahagún and in 1565 by Nicholas Monod in the infusion known as lignum nephriticum. It was derived from the wood of two tree species, Pterocarpus indicus and Eisenhartia polystachya. The chemical compound responsible for this fluorescence is matlaline, which is the oxidation product of one of the flavonoids found in this wood. In 1819, Edward D. Clarkin in 1822 René Just-Horai described fluorescence in fluorites. Sir David Brewster described the phenomenon for chlorophyll in 1833 and Sir John Herschel did the same for quinine in 1845. In his 1852 paper on the refrangibility of light, George Gabriel Stokes described the ability of fluorspar and uranium glass to change invisible light beyond the violet end of the visible spectrum into blue light. He named this phenomenon fluorescence. I am almost inclined to coin a word, and call the appearance fluorescence, from fluorspar, i.e., fluorite. As the analogous term opalescence is derived from the name of a mineral, the name was derived from the mineral fluorite. Some examples of which contain traces of divalent europium, which serves as the fluorescent activator to emit blue light. In a key experiment he used a prism to isolate ultraviolet radiation from sunlight and observed blue light emitted by an ethanol solution of quinine, exposed by it. Physical principles. Photochemistry. Fluorescence occurs when an orbital electron of a molecule, atom, or nanostructure relaxes to its ground state by emitting a photon from an excited singlet state. Excitation. Fluorescence. Here is a generic term for photon energy with H equals Planck's constant and equals frequency of light. The specific frequencies of exciting and emitted light are dependent on the particular system. S0 is called the ground state of the fluorophore, and S1 is its first excited singlet state. A molecule in S1 can relax by various competing pathways. It can undergo non-radiative relaxation in which the excitation energy is dissipated as heat to the solvent. Excited organic molecules can also relax via conversion to a triplet state, which may subsequently relax via phosphorescence, or by a secondary non-radiative relaxation step. Relaxation from S1 can also occur through interaction with a second molecule through fluorescence quenching. Molecular oxygen is an extremely efficient quencher of fluorescence just because of its unusual triplet ground state. In most cases, the emitted light has a longer wavelength, and therefore lower energy, than the absorbed radiation. This phenomenon is known as the Stokes Shift. However, when the absorbed electromagnetic radiation is intense, it is possible for one electron to absorb two photons. This two-photon absorption can lead to emission of radiation having a shorter wavelength than the absorbed radiation. The emitted radiation may also be of the same wavelength as the absorbed radiation, termed resonance fluorescence. Molecules that are excited through light absorption or via a different process can transfer energy to a second, sensitized molecule, which is converted to its excited state and can then fluoresce. Quantum yield. The fluorescence quantum yield gives the efficiency of the fluorescence process. It is defined as the ratio of the number of photons emitted to the number of photons absorbed. The maximum fluorescence quantum yield is 1.0. Each photon absorbed results in a photon emitted. Compounds with quantum yields of 0.10 are still considered quite fluorescent. Another way to define the quantum yield of fluorescence is by the rate of excited state decay, whereas the rate constant of spontaneous emission of radiation is the sum of all rates of excited state decay. Other rates of excited state decay are caused by mechanisms other than photon emission and are, therefore, often called non-radiative rates, which can include dynamic collisional quenching, near-field dipole-dipole interaction, internal conversion, and intersystem crossing. Thus, if the rate of any pathway changes, both the excited state lifetime and the fluorescence quantum yield will be affected. Fluorescence quantum yields are measured by comparison to a standard. The quinine salt, quinine sulfate in a sulfuric acid solution is a common fluorescence standard. Lifetime. The fluorescence lifetime refers to the average time the molecule stays in its excited state before emitting a photon. Fluorescence typically follows first-order kinetics, whereas the concentration of excited state molecules at time is the initial concentration and is the decay rate or the inverse of the fluorescence lifetime. This is an instance of exponential decay. Various radiative and non-radiative processes can depopulate the excited state. In such case, the total decay rate is the sum over all rates. Whereas the total decay rate, the radiative decay rate and the non-radiative decay rate. It is similar to a first-order chemical reaction in which the first-order rate constant is the sum of all of the rates. If the rate of spontaneous emission, or any of the other rates are fast, the lifetime is short. For commonly used fluorescent compounds, typical excited state decay times for photon emissions with energies from the UV to near-infrared are within the range of 0.5 to 20 nanoseconds. The fluorescence lifetime is an important parameter for practical applications of fluorescence such as fluorescence resonance energy transfer and fluorescence lifetime imaging microscopy. Jablonski diagram. The Jablonski diagram describes most of the relaxation mechanisms for excited state molecules. The diagram alongside shows how fluorescence occurs due to the relaxation of certain excited electrons of a molecule. Fluorescence anisotropy. Fluorophores are more likely to be excited by photons if the transition moment of the fluorophore is parallel to the electric vector of the photon. The polarization of the emitted light will also depend on the transition moment. The transition moment is dependent on the physical orientation of the fluorophore molecule. For fluorophores in solution, this means that the intensity and polarization of the emitted light is dependent on rotational diffusion. Therefore, anisotropy measurements can be used to investigate how freely a fluorescent molecule moves in a particular environment. Fluorescence anisotropy can be defined quantitatively as whereas the emitted intensity parallel to polarization of the excitation light and is the emitted intensity perpendicular to the polarization of the excitation light. Fluorants. Strongly fluorescent pigments often have an unusual appearance which is often described colloquially as of neon color. This phenomenon was termed farbing lit by Hermann von Helmholtz and fluorants by Ralph M. Evans. It is generally thought to be related to the high brightness of the color relative to what it would be as a component of white. Fluorescence shifts energy in the incident illumination from shorter wavelengths to longer and thus can make the fluorescent color appear brighter than it could possibly be by reflection alone. Rules. There are several general rules that deal with fluorescence. Each of the following rules has exceptions, but they are useful guidelines for understanding fluorescence. Kasha-Vavilov rule. The Kasha-Vavilov rule dictates that the quantum yield of luminescence is independent of the wavelength of exciting radiation. This occurs because excited molecules usually decay to the lowest vibrational level of the excited state before fluorescence emission takes place. The Kasha-Vavilov rule does not always apply and is violated severely in many simple molecules. A somewhat more reliable statement, although still with exceptions, would be that the fluorescence spectrum shows very little dependence on the wavelength of exciting radiation. Mirror image rule. For many fluorophores, the absorption spectrum is a mirror image of the emission spectrum. This is known as the mirror image rule and is related to the Franck-Condon principle, which states that electronic transitions are vertical. That is, energy changes without distance changing, as can be represented with a vertical line in Jablonski diagram. This means the nucleus does not move and the vibration levels of the excited state resemble the vibration levels of the ground state. Stokes shift. In general, emitted fluorescent light has a longer wavelength and lower energy than the absorbed light. This phenomenon, known as Stokes shift, is due to energy loss between the time a photon is absorbed and when it is emitted. The causes and magnitude of Stokes shift can be complex and are dependent on the fluorophore and its environment. However, there are some common causes. It is frequently due to non-radiative decay to the lowest vibrational energy level of the excited state. Another factor is that the emission of fluorescence frequently leaves a fluorophore in a higher vibrational level of the ground state.